Now talking a little bit about architectures. In our case, we used a really simple architecture, right? We started with a fully connected layer. So we went from 3 inputs, x, y, what do you think is the third? Time, right? Normalized time. What is xy? Xy is essentially, you have your Swiss roll, right? Looking something like this. Xy is any of the points from your Swiss roll, because that's your data. And now you're going from this 3 to how much? To hidden dim, right? So whatever your hidden dim is, let's say we use 64. Then we put a ReLU here. So we put a ReLU here. And then from 64, we go again to, let's say, 64. We again put a ReLU here, right? And from here, from 64, we again go to 64. And then from there, we go to 2, right? So from there, we again go to, let's say, 64. And then from there, we go to 2. And this 2 is essentially our noise. This is essentially the noise for x and y, right? How much noise is present at this time steps t is what the model will output. So this is what our model looks like. But today, I mean, in modern, let's say if you want to do something real, you would start with something like a UNet. So this UNet is essentially an hourglass network. There are these skip connections. I'll show you an image in a second. And this UNet essentially is, what is doing your denoising. So your input is your input image, let's say x0. You add your positional encoding to all these layers, and you are basically going down and then going back up again. You also use these kind of architectures, the UNets, for, let's say, human pose estimation. Because in human pose estimation, you want to predict, let's say, a bright spot where the body joint is. Or you use it for semantic segmentation, because in semantic segmentation, the size of the output is the same as the size of input, and every pixel in the output has a label of the class that it belongs to. So every pixel have a label such as a person, a car, sky, vegetation, etc. Right? So this is the kind of network you use, and they downsample the image to capture global context, and then again upsample to reconstruct the fine pixel level details, and you don't lose information while doing it because you have these skip connections. And then the major paradigm shift happened when we started using diffusion models. Transformers for diffusion models, and this came about in Stable Diffusion 3 or models like Sora, where we are replacing units with diffusion transformers, these DIT blocks. And by treating image patches like words in a sentence, DITs scale predictably and handle global context, global image coherence much better than standard convolution. Another thing that happens is, especially when you use these DITs, what you do is you don't directly work with pixels. You use your VAE. You take the latent in the middle of the VAE, right, which is of lower dimension as compared to your input. And then you patchify it. Let's say this is what it looks like. Let's say it's, 4x4 output. And this 4x4, you would patchify. You would take this patch, and those 4 numbers, you would create a vector out of it. And this is your token. Then you would take the next patch. Let's say we are taking non-overlapping patches, and then you would create the next token out of it. So in modern diffusion models, when you use transformers, you use a VAE to create the tokens of the sequence that go into the transformer inside the diffusion model. Yeah, so this is something that we should know, and all modern methods are essentially, transformer based models. What we still did not, cover is conditioning. How do we condition like we do for GANs? And it's pretty straightforward. If you are using, let's say, transformers, you can use cross attention. You can use, let's say, the KVs from the condition and the Q from the diffusion model, or vice versa, right? Depends what the encoder is and what the decoder is. You can also, if you're using just, let's say, CNN, you can use that just as an additional vector as input. How you input it is, a matter of architecture choice. Another thing that you should definitely look up, and which we'll mention in the rabbit hole section of this lecture, is something called as control net. And control net is something very, very cool. And what you're saying is that, text itself is not enough for precise geometry, and control nets lock the main model and train a small side network to inject these spatial constraints. This allows you to feed edge maps, depth maps, or even human pose heat maps directly into the generation process to dictate the exact physical layout of the output. So now inside the diffusion model, you're, for example, able to input a stick figure such as this. And because it's trained with these pairs, you then are able to generate a human in this pose. Similarly, if you just give it edge images of a bird, you're able to generate an image of that bird for which you have given the edge image, the drawing. You remember the example of the shoe of the pix-to-pix paper that we spoke about in GANs? This is what you can do with control nets. And then there is also this one additional thing that you will hear about in the context of diffusion model is CFG, classifier-free guidance. And the idea here is simple, that when you have this conditioning, what you want to do is you want to train. During training, you will sometimes mask it off. Sometimes you will not provide this conditioning. And what that will do is it will force the model to create something even without the conditioning. So it will not kind of overfit on the conditioning. And then at test time, what you're going to do is you're going to do two forward passes, right? You're going to do two inferences. One, you would do the unconditional, so without the condition, and one where you would do with condition. And what you're going to do is you're going to use the, so let's say this is, your vector for your unconditioned, and this is, let's say, your vector for the condition. And when you're doing the condition minus unconditioned, this is your vector for the condition minus unconditioned. And then what you're saying is you want to take a step from in the direction of the unconditioned, and then you want to add some CFG scale, right? So you want to get to, so this is again a hyperparameter, and what you are saying is the more the CFG forces, the more to listen. We run the network twice at every step, once with the text prompt and one without it, and then you decide how much you want to go in the direction of the conditioning, right? How much you want to go in this direction, and this is decided by the CFG scale. And then diffusion is a really, really slow algorithm, right? Because you're doing literally 1,000 times forward prop of your network. So next, in recent days, there are advances on how to make that fast, how to, optimize all of that. But I will just leave that for, our next courses, where we dive deeper into it, where we kind of train these large scale models such as Flux, and you need to use things like, accelerate, 0, 1, 2, 3, train on large scale GPUs, at least H800s for, let's say, the Flux family of models, and so on. But here, what I wanted to kind of get through was that diffusion is happening a lot today. It's happening in images with the likes of Midjourney, DALL-E, Nano Banana. It's happening with video with the likes of, Sora, VO3. It's happening in audio and music, Suna. It's happening in 3D and science, so protein folding, drug discovery, and generating 3D assets for gaming. It is happening for motion and also for 3D humans. It is happening for robust trajectories of VLAs, for example, in AlphaMeo R1. So there is some trajectory that gets generated, and then finally they put it into a diffusion model to then denoise it. Right? So it's really very generic. The only downside is it is slow, and there's a lot of research happening where we try to kind of do it in a fast way. We, Siddharth and I, Sridhar, we have done it for human pose estimation, and I invite you to look at our paper Odo. And in there, what we have done it, we kind of have human pose So human pose changes are easy, but human shape changes are harder. So what we do is you give it an image of a human. It goes into this conditional diffusion model, and then what comes out, and then you also give it, some inputs on how you want to change it. You want to make it fatter, and out comes your image of a person who is fat. And how we do it is, again, maybe a topic for another day, but I invite you to look at the blog, to look at the paper. But now that you understand this diffusion model, you will easily understand what we are doing there. And we use a UNet, we kind of, so it's pretty straightforward. And this would also be kind of a test of your understanding. Are you able to understand that paper from what you have learned here? And I'm sure you will. Thank you.